Hey everyone, welcome back to another lesson in calculus. Today we're going to be talking about how to take derivatives of functions without using the really long definition of derivative, right? You remember the f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. That's a long process and it can get really tedious, especially when you get to more complex functions. So today we're going to talk about some basic rules that will help us to alleviate the use of that, eliminate the use of that. And to do so, what we need to do is prove these rules, right? That's just a logical thing. We can't use a rule without actually proving it. We're going to prove some of these rules, and then we can start using those rules in places to make our differentiation process a lot simpler. So with that said, the main title for today is the power rule because that's the big one for today. But we're going to get into a couple other ones before we get into the power rule. Okay? So the first one, we're talking about the rules of differentiation, is dealing with constant functions. So if I have a constant function like f of x equals any constant, like 10, pi, negative 17, 4.257, what is the derivative of a constant? Well, we should be able to conclude pretty easily that the derivative of a constant must be 0. And if you think about that, the reason that the derivative of a constant is 0, I'll give you a quick example. If I say y equals 4, 4 is a constant line. It's a horizontal line. That's any constant function. So what's the derivative or what's the slope of a horizontal line? The slope at every single point along that line is 0. So the derivative of any constant, any horizontal line, is 0. That should be an obvious thing. Now, with that said, we can conclude that y prime is 0. With that said, let's go ahead and take a look at a proof for this. So we would say that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And so then we go to plug this in. When we go to plug x plus h into our function, well, what do we get out? I'm going to get a constant out. There's no x to plug into, and so we just get the constant left over. So limit as h approaches 0 of some constant minus, what do I get when I plug in the x value to f of x? Well, I get the same constant because it's a constant. And then from here we can see it pretty easily, I believe. C minus c is 0 over h. And then what we would tend to want to do is substitute 0 in. And so we end up with 0 over 0 as indeterminate. But before we even go there, what we need to realize is this, that this 0 is an actual 0, okay? This h value, when I'm plugging in 0 to determine my limit, is not actually 0, it's just infinitely close to 0. So you remember that 0 over 0 is indeterminate, but that's not what we actually get here. We actually get 0 over some number that's really close to 0. And you remember that 0 divided by any number other than 0 is 0. And so we can say that f prime of x is 0. Okay, so pretty straightforward, pretty easy, pretty obvious, I think. Okay, and the proof of that is also there on the lesson. Here's another quick example of this, really simple, that if f of x equals 17, then what is the derivative of f? Now, normally, the only reason I'm bringing this up, because you already know the answer is 0. The only reason I'm bringing this up is because we normally write the derivative as f prime of x. So we know it's 0. Remember, this is Newton notation. Newton's notation for the derivative doesn't really explain what's going on. And so I wanted to express it in a different way. The question is, what is df dx? Well, that is the same as, in a sense, taking the f out, and so we say d dx of f. What is the derivative of f in respect to x is what we would say. And if you want to see it a little different, we can say, remember, d actually stands for delta, lowercase delta. So that's the very small change in f over the very small change in x. So it's a slope, the change in y over the change in x. So there's the derivative, the very small change, the very small slope. And so we can see as a result of that, that is going to be 0. Okay? So that's pretty straightforward. Let's go ahead and go on to a different rule now. The constant multiple rule. The constant multiple rule. The constant multiple rule says that if I have a function that is related to a different function by the multiple of a constant. So in other words, if f of x is equal to a constant times some other function, then the derivative of this would be, the derivative of f would be the constant times the derivative of that function. Now, we don't want to overgeneralize this because this doesn't, the things that are going on in your brain right now about constants or about multiplication, you're trying to make this connection with multiplication. Don't. It's a connection about constants being multiplied, not just multiplication. Okay, here's generally what the idea says. If I have a function and I want to take its derivative, what I need to do is take out any multiplication, any constant that I'm multiplying, take it out, ignore it, okay? Just completely ignore it. Take the derivative of the thing that's left over and then multiply it back by that constant. Bring that constant back in and multiply it. So I guess the biggest, the best example or an example of this is, let's say that y equals 7 times x squared. 7x squared. Do we have a constant multiple? Yes, we do. The constant multiple is 7. So what does this say to do? It says to take the derivative of y, the first thing we have to do is take the derivative of x squared. So we'd write it like this: d dx of x squared. Whatever that derivative is, take it and multiply it by the 7. Okay? Or another way to write this is that the derivative in respect to x of 7x squared is the same as 7 times the derivative of x squared. Okay, so take the constant out, take the derivative of what's left over, and then multiply it by the constant. Okay, now I haven't proven that to you yet. I'm just explaining to you what it is. Let's go ahead and take a look at the proof. If I want the derivative of f, we'll use the difference quotient expression of f of x plus h. And you notice that I write this down every time. It helps me to see what I'm plugging into as I go along. So this would be the limit as h approaches 0 of f of x plus h. Well, f of x is c, a constant, times g of x. So that would be c times g of x plus h, and then minus f of x, which is c times g of x, all right, all over h. And then from here, we can see that both terms in the top have a common factor of c. So we could say the limit as h approaches 0 of c times g of x plus h minus g of x, and then all over h. And so you could start seeing how this is going to formulate here, because there is my normal difference quotient, right? Now I'm going to rewrite this to say this. I'm going to take the constant out and say the limit as h approaches 0 of c times g of x plus h minus g of x all over h. And so all I did was I took the c out front of this fraction. Now we have a rule in limits that says that if I'm multiplying two things and I want to take the limit of that multiplication, that's the same as multiplying the limits. In other words, the limit of a product is the product of the limits. Okay, so that's the same as saying the limit as h approaches 0 of c times the limit as h approaches 0 of g of x plus h minus g of x all over h. Okay, so there's what we have so far. Now, what is the limit as h approaches 0 of a constant? What is that limit? Not what is the derivative, but what is the limit of a constant? Well, if a constant, let's say this is my constant, what is the limit as h, if this is my h-axis, if you would, okay? What is the limit of that constant as, as h approaches 0? So as I move h closer and closer to 0, then what is that value? That height is c. So the limit of a constant is the constant. And now here's what's kind of cool. What is this? What is the limit as h approaches 0 of g of x plus h minus g of x all over h? That is the definition of the derivative for the g function. So that's g prime of x. So you can see that if f of x is a constant times a function, the derivative is the constant times the derivative of that inner function, if you would, or that function that's being multiplied. Okay, so that's the proof for the derivative of constant multiples. Another way to look at that, you can see that I used u as the function. So instead of calling it g of x, I just called it u. An example of this would be f of x equals 5 natural log of x. Do we have a constant multiple? Yes, we do. So we can take that constant multiple out and find the derivative of what's left over, the natural log of x, and then whatever that is, multiply it by the 5. Now, I put question marks here, saying we'll get to it later, but in fact, you already should know the derivative of natural log of x. We kind of explored it in a previous lesson. So I'll go through this a little bit more. If I have f of x equal to 5 natural log of x, this is a constant multiple. Therefore, f prime of x is equal to 5 times the derivative, times the derivative of natural log of x. Okay? And then we know, okay, we carry that 5 down. What's the derivative of natural log of x? You guys should know that it's 1 over x. Okay? We explored that. I haven't proven it to you yet, but we kind of explored it the other day. And so this is just another example of a constant multiple. All right, let's go ahead and take a look at, we're going to kind of explore something here with our calculators. It says use your calculators to determine the derivative of the following functions. So remember I told you in the lesson about how to find derivatives with the calculator. I said don't ever use your calculator to find the derivative function. Only use your calculator to find the derivative at a point. Well, today I want you to use your calculator to find the derivative function of each of these because I want us to see a pattern based on what we get with our calculator. So if you remember the keystrokes to find a derivative, let's go ahead and just look at the first one. That says x cubed, I believe. Yeah, x cubed. So we have f of x equals x cubed. So to type that in to get the derivative function, you find the derivative, which is second 8, or you can also push, let's see, get you the right one, push f3 and then differentiate. So that brings up the derivative with the parentheses. Then you'll type in your function. So you would type in x caret 3 and then comma x, close parentheses. That will give you your derivative function. If you were looking to evaluate at points, you would put evaluate when x equals whatever. But we're looking for the derivative function. So that's just a reminder of how to do that. So go ahead and pause this, and I want you to find the derivative of each of these and write them down from your calculator, and then we'll come back and talk about some patterns that we should see through this. So for group 1 here, and normally I would separate you guys into separate groups, and then we would come back together as a whole group. But f of x equals x cubed, you should have gotten f prime of x equals 3x squared. For y equals radical x, you should have gotten y prime equals 1 over 2 rad x. That's kind of a weird one. Talk about that in a second. For group 2, g of x equals x to the 5th. So g prime of x should equal 5x to the 4th. And then y equals the cube root of x. Now, what you get in your calculator might be a little bit different than what I write down, but you should have gotten something that's equivalent to 1/3 x to the negative 2/3. Okay, maybe it was written as 1 over 3x to the 2/3, maybe something like that. Okay, and then group 3 for h of x, you should have gotten, for the derivative, you should have gotten 12x to the 11th. And then for y equals the 5th root of x, y prime should have either been 1/5 x to the negative 4/5, or maybe it was written as 1 over 5x to the 4/5, just depending on what your calculator, how your calculator calculated those things. So I think the point that I'm trying to make is we're trying to observe a pattern, a relationship here, dealing with when I'm giving you a function where the base is a variable and the exponent is a numeric value. You go, well, I see that here and here and here. The base is a variable and the exponent's numeric. What's going on here? Well, remember, rad x is the same as x to the 1/2. and then cube root of x is x to the 1/3, and then fifth root is x to the 1/5. So all of these have something in common. All of their bases are variables, and all of their exponents are numeric values. From there, we should be able to see some sort of pattern that can help us determine the derivative. And hopefully you've already seen it. Looking at, and this one I'm going to go ahead and rewrite this way as well. This should be rewritten, or could be rewritten as 1/2 x to the negative 1/2, like this. Okay. So what do you see? Well, you can see that in every case, the exponent from the original function to the derivative is reduced by a value of 1. So this exponent's 5, the derivative of the exponent is 4. This exponent's 1/5, the derivative's exponent is negative 4/5. We're subtracting 1 from the original function to the derivative function. So that's the first thing. The second thing you should note, and these are really basic ones so you can see it, that the derivative of x cubed, it wasn't just that we subtracted 1 from the exponent and got squared. It's that we took the exponent and actually moved it to the front on top of it. So we take the exponent 3, move it to the front, and subtract 1 from the exponent for our new exponent. Okay? See that here? X to the 1/2, I move the 1/2 to the front, and then I subtract 1 from my prior exponent to get my new exponent. Take the 5 here, move it to the front, and then subtract 1 to get my new exponent. And that's true all the way throughout this entire thing. Now that doesn't prove it. That is an example. Those are 6 different examples of it, and we can see a pretty good pattern. Again, it doesn't prove it, but it gives us a good idea of what's really happening. And so let's talk about this more in general. Let's go ahead and talk about this more in general. This is called the power rule. And so here it is, right? Here it is. When I was a little tiny boy, I had an action figure called He-Man. And He-Man, the cartoon He-Man, he'd always walk around with this sword, and big muscular guy. And whenever he had to fight the evil powers of Skeletor, he would raise his sword and he would say, "I have the power!" Right? Sorry, a little embarrassing, but that's okay. The power rule. Well, guess what, ladies and gentlemen? You now have the power. You have the power rule. And this will make your lives as taking derivatives so much easier. And probably not easy to see right now because the lights went out, so let me fix that. But the power rule is so essential in what we do in calculus. Obviously, there's going to be a lot of other rules when we talk about derivatives, but this one is so important. The bottom line is this: f of x equals x to the n. Then we can conclude that the derivative, what did I just say about the power rule? You take the exponent and you move it to the front. So you say n times x, and then we subtract 1 from the exponent to get our new exponent. So to the n minus 1. So whatever that numeric n value is, n represents a numeric value, we put it in the front and multiply it by x raised to, the new exponent will be taking the previous exponent and subtracting it by 1. So let's go ahead and take a look at a quick example of this. In this case, we have the derivative in respect to x of x to the 22nd. Well, that would be 22x to the 21st. Take that to the front, subtract 1, you have your derivative, 22x to the 21st. Here's another example. If I've got something that looks like this is a good one because it applies 2 rules. What is the derivative? Let me write that down. What is the derivative of 3x to the 5th? Well, wait a minute. That's not the same as that. There's a number in front. Yes, I know. We just dealt with a rule that dealt with constant multiples. Remember, what do we do with a constant multiple? We take it out. We just put it off to the side. And then we take the derivative of what's left over. So the derivative of x to the 5th, essentially. So we take the constant out, 3 times the derivative of x to the 5th. Well, we now know the derivative of x to the 5th is 5x to the 4th. And then we still have that constant out front, so it's 3 times 5x to the 4th, which simplifies to 15x to the 4th, 15x to the 4th. So that is another example of using, this is a combination of the constant multiple and the power rule. So again, taking the constant out, multiplying it by the derivative of the power, and we end up with 15x to the fourth. So go ahead and do some practice on this. See what you come up with on these, and then come back and see if you're correct. For number 1, we're given a pretty easy one, I think. Number 1, it says y equals x to the 6th. So y prime should be 6x to the 5th. Number 2, h of x is equal to 4x to the negative 2nd. So therefore, h prime of x is going to be, now we could take the constant multiple out, take the derivative of x to the negative 2nd, which would be negative 2x to the negative 3rd. We have to subtract 1. Oftentimes, students will add 1. They'll put x to the negative 1st because they think, oh, I got to get a smaller number, so 1's smaller than 2. These are negative numbers, right? So that's the derivative of this guy, but then we have to multiply it by the 4. So we end up with negative 8x to the negative 3rd. Okay. Number 3, we've got take the derivative in respect to x of 5 over x cubed. You go, I don't know how to do that. Well, I know. I have an idea, some students might say. I know what to do. That's a constant on top, so I'll just put a 5 on top, and then I'll take the derivative of the bottom, so that's 3x squared. That is not correct. Okay? That is not a rule that I gave you. This is dealing with, what's going on here? This is dealing with a variable in a denominator. All the power rule says is the derivative of a power expression, of a polynomial expression, or when the base is a variable and the exponent is a numeric value. This is in the denominator. We can't do that way. So actually what we have to do first is rewrite this so that it can get into a form that I'm familiar with. And so to do that, remember, we make the exponent negative. So this is the same as saying the derivative of 5x to the negative 3rd. We just move that exponent to the top. From here, we have a constant multiple. So when I take that derivative, I'm going to pull that 5 out, then take the derivative of x to the negative 3rd. So I'd end up with negative 3x to the negative 4. And then multiply those out, so I get negative 15x to the negative 4. And if you wanted to write it as a whole number or a positive number exponent, it would be negative 15 over x to the 4th. You can see that that would be different than the way I showed you before. So you have to make sure when you're using the power rule that the variable is not in a denominator, okay? We're going to get more into those rules later. When we deal with quotient, we're going to talk about the quotient rule and the product rule, dealing with a little bit more complex derivatives. All right, so number 4, we've got x of t equals 8 rad t. Well, we have to be able to write this so that this is a numeric exponent. So x of t is equal to 8t to the 1/2. Then the derivative of that is going to be, take the constant out, multiply it by the derivative of the power, so it would be 1/2 t to the negative 1/2, and then we can multiply those together. 8 times 1/2 is 4, and so we end up with 4t to the negative 1/2. And if you want to write it so that's a positive exponent, it would be 4 over t to the 1/2, or 4 over radical t, okay? But this is fine to write it like that. You might notice this little quick pattern. All you have to do is take that exponent and multiply it by the coefficient. So negative 2 times 4 is negative 8, then subtract 1 from the exponent, okay? Same thing here. Negative 3 times 5 is negative 15, subtract 1 from the exponent. Here, 1/2 times 8 is 4, subtract 1 from the exponent, right? Here we actually have a coefficient of 1, so we can multiply that. 6 times 1 is 6, and then subtract 1 from the exponent. So that's the power rule. And those are 4 separate examples of how to apply the power rule, okay? Now, as far as the proof goes for this proof gets kind of wonky, because when we're talking about a polynomial expression, we could have, if I were to say, let y equal, well, let me use a function, f of x equal x to the n, where n is a numeric value, okay? Where n is a number. To find the derivative using the definition, we have the limit as h approaches 0 of f of x plus h minus f of x all over h. And then plugging that in, x plus h, we'd end up with x plus h to the n power minus x to the n power all over h. Oops, I forgot my limit expression. Limit as h approaches 0. Okay. Now from here, it kind of becomes a little bit difficult to see unless you're familiar with the Pascal's triangle. Oops. Pascal's triangle, dealing with raising a binomial to a whole number value, if you would. And this is only dealing with whole number values. The idea is that this is when you would get this pattern when n equals 2, when n equals 3, when n equals 4, and so on, dot, 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 dot. What I notice here is that the second term always has the same coefficient value. So I'll give you an example here. If I said x plus 1 squared, if I square that, I get x squared plus 2x plus 1. You'll notice that the coefficient in the x squared is a 1, the coefficient on the middle term is a 2, and then the constant at the end is 1. Technically what this is x to the 0 power. Okay? If I want to say x plus 1 cubed, x plus 1 cubed is actually x cubed plus 3x squared plus 3x plus 1. And again, we can write that with a coefficient of 1 here, and then an x to the 0 there. The point is, as you go through this, if I expand this and multiply it all out, I'm going to end up with the limit as h approaches 0 of x to the n, because the first term in any of these, no matter what n is 1, the coefficient's 1. Then the next term will be plus some constant value, we'll call it a, some constant value, times h, I'm sorry, the constant value is 4. So 4 times h times x to the n minus 1, because remember we subtract 1 as we go down. And then we can keep going with that, and it's not necessarily 4, I misspoke, that's if n is 4. Well, it depends on what n is. N is 4, the next one would be 5, this would be the n value, and the coefficient there. And then that can keep going, and at the end, we would end up with h to the n here, and then minus x to the n all over h. The first term and the last term go away, and then all of these other terms have h in them, okay? And as time goes on, and I kind of missed a few, but the next term would actually be like this. It would actually be some constant value, whatever this constant value is, times h squared times x to the n minus 2, and then plus another constant times h to the third times x to the n minus 3, and so on and so on and so on, until we get to the last term, which is h to the n. Again, all of them have a factor, and then minus x to the n at the end for that one. Those will always cancel out, the x to the n's always cancel out, and then all of these have an h as a factor. And so if I factor out an h, that h is going to go away, and we're left with n times x to the n minus 1, plus in this case a times h to the first times x to the n minus 2, plus some constant times h squared times x to the n minus 3, plus dot, 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 and then this one would be h to the n minus 1, okay? And then we're taking the limit as h approaches 0. Well, if I plug in 0 for h on all of those are all going to go away. 0 times any of that, 0, 0 times all that, 0 times all that. So that's all going to go away, and we're left with n times x to the n minus 1, which is exactly what the derivative is. Take the exponent, multiply it to the coefficient in the front, and then subtract 1 from the exponent. Like I said, the proof of this is really kind of wonky, and it's dealing with having a good grasp of Pascal's triangle and how it deals with multiplying binomials or raising binomials to any whole number power. But with that said, let's go ahead and take a look at something else on top of the power rule. So this is kind of cool. I really like this. This blew my mind because I love how mathematics all ties together. You would think that math would have a problem every once in a while, or a lot. That okay, if this is a rule in math, does it work every time? And does it express itself well enough to be acceptable in a sense. And you'll see what I mean in a second. I know that kind of sounds weird. But if I look at f of x equals rad x, f of x equals rad x, and I say, okay, what's the domain? The domain of this guy, we know the domain is from 0, including 0, to infinity, right? So I can plug in 0 and take the square root of 0 and get 0. That's fine. But if I ask for where this function is differentiable, you know that this function kind of looks like this. A function is not differentiable at an endpoint. A function is not differentiable at an endpoint because you need to be able to approach that endpoint or approach the point that we want the slope at from the left and from the right. So if I have a curve that looks like this and I say find the slope at this point, technically, remember the left-hand derivative and the right-hand derivative, or the left-hand slope, has to match the right-hand slope. In this case, you can't get a left-hand derivative because there's nothing to the left of 0. So if I were to ask you for where this function is differentiable, this function is differentiable for all values that are greater than 0, not including 0. 0 is not, it's not differentiable at 0 because I can't take a left-hand derivative at 0. But I can take a left-hand derivative at any point to the right of 0. Okay, so keep that in mind. Now it says, what is f prime of x? Well, remember, we're going to rewrite this as x to the 1/2 power. So when I take the derivative of this, I end up with 1 over 2 x to the negative 1/2, right? 1/2 x to the negative 1/2. If I rewrite that, I end up with 1 over 2 radical x. And then I would say, and I'm asking here, what is the domain of f prime of x? Well, the domain here, some might fall into this category that this is the domain. That's not true, because if x is 0, you can't divide by 0 here. So really the domain of this guy is 0 to infinity, not including 0. That really blows my mind, and you should be able to go, oh, that's really, really cool. That this function is only differentiable over this interval, or this domain. So you would expect, if calculus was really good at what it does, that when I take the derivative, that the domain of the derivative should match when the function is differentiable. And it does. It fixes, or it addresses that problem of non-differentiability at 0 because we're dividing by 0 if we try to do that. So that's like, that's so cool to me. And so I'm going to draw stars, and I'm going to circle it, and I'm going to say that is awesome, right? How does that happen? How does that just happen? Okay, and it happens a lot throughout a lot of calculus, where taking the derivative or doing something with calculus expresses the concerns that you might have with your original function. Okay, it's amazing to me. All right, the last rule I believe that we're going to cover today is called the sum and difference rule. The sum and difference rule. The idea is this, and you can look at that and kind of get confused, but the idea is this. If I have a function, f of x plus g of x, so if I have two separate functions, if you would, the derivative of this, so the derivative in respect to x of this guy, is going to be f prime of x plus g prime of x. That seems like common sense, okay? That seems like common sense. That the derivative of a sum of two separate functions is the same as just taking the derivative of those two functions and adding them together. Same thing with subtraction, so I'll put a minus sign there. A quick example of this would be something like 5x to the 7th minus 3x squared. If I want the derivative of this, guy, all I have to do is take the derivative of the first thing and the derivative of the second thing, and then perform the operation between them. So the power rule here, we get 35x to the 6th. And then the power rule here, we get 6x to the first, or 6x, and then we have the minus sign in between. And that's our derivative. That's the sum and difference rule. In order to take the derivative of a sum, you just take the derivative of each piece and then add it together. Or same thing with the difference, subtract it. Okay? Now, with that said, and that's important for polynomial expressions or anything where we're adding and subtracting things. So the derivative of this guy, I'm not going to go over it on the board here. The derivative of this guy is going to be negative 2x, and then plus 6. And then now what's the derivative of negative 5? Well, remember, negative 5 is a constant. What's the derivative of a constant? It's 0. So we'd say plus 0 there. But that doesn't affect the final answer. Okay? And so go ahead and do a practice problem here. Find the derivative of p in respect to t. And then push play to see if you got the answer right. In this case, we got p equals t cubed plus 6t squared minus 5 over 3t plus 16. And so the derivative of this is going to be 3t squared plus 12t minus 5/3 plus 0, if you would. And we don't have to put the plus 0. We can just cancel that out. So that's p prime there, okay? And I have that right. All right, now the proof of this, there's the bell. The proof of this is going to look, well, maybe I should do this on the board. If I have two functions that I'm putting together to get a separate function, I've got f of x equals, the two that I use here are g and k. G of x plus k of x. If I want the derivative, we take the limit as h approaches 0 of f of x plus h minus f of x all over h. Now we'll plug in what we know. So the limit as h approaches 0, I plug in x plus h into my x value. So I have to do it to both of those. So I end up with g of x plus h plus k of x plus h. That's this part. And then minus f of x. So it's minus g of x plus k of x. One thing you got to be very careful of is that you're putting brackets or parentheses around this because you're subtracting the whole function, if you would. Okay? And then we distribute that negative, and we can rearrange things. I'm going to do this pretty quickly. Distribute the negative, and you're going to see how I can rearrange this. This will be g of x plus h minus g of x, and then plus k of x plus h minus k of x all over h. And then I can separate this into two separate limit expressions. So I could say g of x plus h minus g of x all over h, and then plus the limit as h approaches 0 of k of x plus h minus k of x all over h. And so because I'm summing two, or I'm taking the limit of a sum, I can separate that. Now I could separate it more, but I didn't want to because this is recognizable. This first term, the limit as h approaches 0 of this is just g prime of x. And then the limit of this term is just the derivative, we call it the derivative of k of x. So f prime of x is equal to g prime plus k prime if f is equal to g plus k. So that's the proof of that guy. Pretty easy, I think, overall. But you can see that anytime you add or subtract functions, to take the derivatives, you take the derivative of each piece and add or subtract. The last problem here, exit problem, the question is x of t differentiable at t equals 1? So go ahead and give this a shot, and then come back and see how you did. Hopefully you do pretty well on this. All right, so for this guy, for radical t minus 1.5, and that's for t is greater than or equal to 1. And this is x of t. And I know we can get lost. Oh, that's an x. X is now our function, and t is our variable. We want to know if the function is differentiable at t equals 1. So what we need to do is check all the things that are required for a function to be differentiable at a point. Remember that x must be continuous when t equals 1. That's the first thing. We also need to check to see x prime of 1 from the left is the same as x prime of 1 from the right. And then we also have to see if x prime of 1 is equal to plus or minus infinity, or not equal to plus or minus infinity. So we got to check all these things. So the first thing I'm going to do to check for continuity is the limit as x approaches 1 from the, sorry, t approaches 1 from the left of x of t. Plugging in 1 to the top, we would end up with 1/2 of 1 to the 4th minus 3 times 1 plus 5. So we got 1/2 minus 3 plus 5, so that's 2.5. or 5 halves, I believe. 2.5, yeah, 5 halves. Okay, we got to check our limit from the right. And again, this is just checking for continuous. So we'll check for the other things in a second. Okay. So we would check there. So that'd be 4 times radical 1 minus 1.5. Radical 1 is 1 times 4 is 4 minus 1.5 is in fact 2.5 or 5 over 2. So we know the limit exists. And the last thing we need to check for is x of 1. We're going to use the bottom function again. Might as well show the work. And so we end up with 5 over 2. So we can say x is continuous when t equals 1. The next thing we need to do is figure out the left and right hand derivatives. Now we know rules, so that's kind of nice. We can write an expression for the derivative x prime. Let me go ahead and do that. X prime of t is going to be a piecewise function, just like this is. So the derivative of this guy is going to be 2t to the third minus 3, and that's for all values t is less than 1. And then the derivative of this guy, that's t to the 1/2. So that'll actually be 2t to the negative 1/2. And the derivative of negative 1.5 is 0. And that's for all values greater than 1. I do not want to put an equal sign here because I don't know if the derivative is the same from the left or the right. So I'm just going to put less than and greater than. Now I'm going to check x prime of 1 from the left. So I'll use the top function. So that's 2 times 1 cubed minus 3, which is negative 1. And then I'll check x prime of 1 from the right. So I'll use the bottom one. So that's 2 times 1 to the negative 1/2. Well, 1 to any power is 1, so that's just 2. So we can see here that x prime of 1 from the left is not the same as x prime of 1 from the right. So we would say x is not differentiable when t equals 1. And we want to give a justification. This is the justification, but what was that called? When the left-hand derivative, the left-hand slope, is not the same as the right-hand slope. So coming in, the slope was negative 1, right? Maybe it looks something like that. And then coming out, the slope was 2. So this is a corner because the two derivatives are not the same and they're not infinity. If they were, remember, different infinities, then it'd be a cusp. If they were the same infinities, then it would be a vertical tangent. But these are, the left and right-hand derivatives are different numeric values. Therefore, it's a corner. All right. All right, so that wraps up this lesson in the power rule and a bunch of different other smaller rules that are going to help us get into more complex things later on. I hope this kind of excites you because now you can do derivatives in a matter of seconds instead of a matter of minutes. And so that's really cool. If you have any questions, please comment below. Otherwise, I will talk to you guys later.